Let's talk about notation. Let's talk about how we write line integrals. So if we've got a vector field, capital F, then we often write the line integral over a curve C in the following way. We write it as the integral over C of the vector field F dot with ds. Or ds is kind of a simple symbol that stands in for velocity. And in this case, that helps us remember that the line integral is gotten by taking the dot product of the vector field where we are with the speed at where we are. All right. So there's a comparison here with path integrals as well. So line integrals and path integrals have similar features and they look kind of the same in some ways, but they're calculated in different ways. First of all, they're integrating different things. Over here, we've got a line integral integrates a vector field. It tells us about transfer of energy, whereas a path integral over here integrates a function, something with one output, and it tells us about, say, mass. We're adding up total density or something like that. The notation for these is a little bit different. It looks very similar, but one is an integral of a vector field dot ds, and one is an integral of a function f with no dot times ds. You'll sometimes see it written that way. The formulas look similar as well, but for a line integral, we're taking velocity and we're taking a dot product. For path integrals, we're taking speed and then we're just multiplying the function by the speed. And the most important part, direction matters for the line integral and direction doesn't matter for the path integral at all. So for the path integral, it doesn't matter if we go forward or backwards along the curve, it has the same arc length. But for a line integral, the energy transfer direction changes. Now, many times you'll see an alternative notation for this. So if we're doing a line integral over a vector field p comma q, where p is the horizontal and q is the vertical component of the vector field, then you'll often see the line integral written as the integral of p dx plus q dy. So for example, if we had the vector field x squared plus y, yx, like so, then this would be written as a line integral of x squared plus y dx plus y times x dy, like so. That's alternative notation. It makes it a little bit shorter to write down. And similarly, if we're in 3D, a line integral of p dx plus q dy plus r dz, this is shorthand for the line integral of the vector field p comma q comma r. Now, the alternative notation is a little bit handy in some ways because it converts more directly into a calculation. What it does is it lets us say, instead of thinking of this as a bunch of separate discrete steps, what we're doing is we're kind of doing substitution. We calculate what dx and dy and all of those are in terms of our time variable t, and we just substitute those in. And we don't have a bunch of extra kind of intermediate looking steps. There's no change in the amount of work, but it can feel very different. So, for example, here's a line integral of a vector field f of xy is equal to y squared comma x over the upper half circle counterclockwise. Inside two-dimensional space, that's a line integral along this upper unit half circle. Going counterclockwise, that's again going to be parameterized by x is cos t and y is sine t, but now t goes between 0 and pi rather than 0 and 2 pi because we're only doing the part that goes from angle 0 to angle 180 degrees. In this case, if x is cos t, then dx is minus sine t dt, and dy, if y is sine t, then, or if y is sine t, then dy is cos t dt. And so we can then take all this stuff and substitute it back into the integral. It becomes the integral of y squared. We plug in y is sine t, and dx is minus sine t dt plus the integral of x is cos t, and dy is cos t dt. And simplifying that, that would be the integral of minus sine cubed t plus cos squared t dt, kind of collecting terms, and then that integral would be from 0 to pi. So by contrast with the method before, we didn't write down like, hey, here's the velocity vector, hey, here's the vector field, let's take their dot product, and then assemble that all. So it does the same thing, but it feels like it has fewer steps. And so some people prefer to use this notation as a way of thinking about and writing about vector fields. And physically, what it kind of says is that, well, how much energy is the vector field giving us if we move? It says, well, if we move a little bit in the x direction, then we get y squared times the amount of we moved in the x direction as our change in energy, and similarly for the y change.